Let us solve a question on utility function. The question is, a consumer's utility function is given by utility is a function of the two goods x1 and x2, which is equal to 2x1 minus 1 raised power 0.25 times x2 minus 4 raised power 0.75. If the consumer has a total budget of $73 and unit price of good x1 and x2 are $2 and $1 respectively, then the value of x1 plus x2 is, we need to find out the optimal value of x1 and x2 combined. Okay, so what we are being given, we are being given a utility function, that is u is equal to 2x1 minus 1 raised power 0.25, it can be written as 1 upon 4. Okay, then we have x2 minus 4, and in place of 0.75 we can write 3 upon 4, simply changing them into fractions. So the endeavor of the consumer is to maximize this utility. Okay, so maximize utility subject to the given budget constraint. And what is the budget constraint? We are being told price of x is being given as price of x1, and let's write it here p1. Okay, price of x1 is being given us here as $2 and price of x2 is being given us as $1, and income of the consumer is being given us as $73. Okay, so consumer wants to maximize this utility subject to the budget constraint. What is the budget constraint for the consumer? Let's write it here. That will be p1, that means price of good 1 times of units of good 1 plus price of good 2 times units of good 2, that is x2, should be equal to the total budget of the consumer. Okay, p1 is 2, so we can write consumer wants to maximize this utility subject to this budget constraint. That is, in place of p1 we have 2, we write twice x1 plus in place of p2 we have 1, so we can write x2 is equal to the income of the consumer, that is the budget of the consumer, which is m, and m is equal to 73. Okay, now graphically what exactly is meant by this? So let us say we have good x1 on the horizontal axis, x2 on the vertical axis with the given budget. Okay, let us say this is a budget line of the consumer. With the given budget, consumer wants to reach to the highest possible indifference curve or highest possible utility. Okay, so with the given budget line, consumer wants to reach to the highest possible indifference curve to maximize his utility or satisfaction. Okay, and it happens the optimal value lies at a point where the slope of the indifference curve and the slope of budget line are equal, and it is a point where they are tangent to each other. Okay, so what is the condition for optimality? That is, the marginal rate of substitution between x1 and x2 should be equal to the ratio of the prices, that is p1 upon p2. Now MRS is, as we know, it denotes the slope of the indifference curve. It denotes the slope of indifference curve, and this denotes the slope of BUD-GET budget line. Okay, now what is MRS? As we know, MRS is simply the marginal utility of good 1 upon marginal utility of good 2. So let's calculate them first. Marginal utility of good 1 means the partial derivative of the utility function with respect to x1. Okay, so with this utility, taking partial with respect to x1 will give us, since we are taking the partials with respect to x1, so x1 is here, so it is raised power 1 upon 4. So first we use power function rule. 1 upon 4 will become coefficient, then we have 2x1 minus 1, and then we have then exponent is subtracted by 1, so 1 upon 4 minus 1 comes out to be minus 3 upon 4. Okay, then we have x2 minus 4 raised power 3 upon 4 times the derivative of this. Okay, first we apply the power function rule here, and then we internally differentiate with respect to x1. So here we will get also 2. Okay, Similarly, marginal utility of good 2 means the partial derivative of utility function with respect to good x2. So this time taking partials with respect to x2, so x2 is in this here. So first the exponent becomes coefficient, so we will get 3 upon 4. 2x1 minus 1 raised power 1 upon 4 will remain same because we are taking partials with respect to x2. Okay, then we have x2 minus 1 raised power, when we exponent is subtracted by 1, 3 upon 4 minus 1 comes out to be minus 1 upon 4, and the derivative of x2 in the brackets is 1. Okay, here we have 1. Now, as we know, let me see if I have the space left. Yes, I do have. So solving these, mu1 upon mu2 is equal to du upon dx1 divided by du upon dx2. So we divide them with each other, and it should be equal to the ratio of the prices, that is p1 upon p2. p1 is being given us as 2 and p2 is equal to 1. Okay, I have divided mu1 and mu2 here to save the space. So here what will we get? Let us see. First thing is we have 1 upon 4 into, it will get reciprocated, it will become 4 upon 3. Then we have 2x1 minus 1 raised power 1 upon 4. Okay, so let's write it here. 2x1 minus 1 raised power 1 upon 4. And when we transpose this to numerator, okay, so let me rewrite it here. It is getting messy here. So what we will do here, first thing is we transpose this term to denominator and this term to numerator. Okay, and let me explain it here, what I am doing here. When I transpose, let us say this term to numerator, what will happen? It will become x2 minus 4 raised power 3 upon 4. Transposing this term, it will become x2. Okay, where is x2 minus 4? Okay, we have here x2 minus 4. Here also it is x2 minus 4. Okay, x2 minus 4. When I transpose this term to numerator, the exponent sign will change, so it will become 1 upon 4. Since bases are same, we can add up the exponent, so it will become x2 minus 4 raised power 1. Okay, so what is happening here? When we solve this stuff, we are getting x2 minus 4, and similarly when we transpose this term to denominator, it will get multiplied with this term and exponents will add up to 1, so we will get 2x1 minus 1. Then we have 1 upon 4 into 4 upon 3 into 2, so this gets cancelled, so it should be equal to 2 upon 1. So also 2 and 2 will get cancelled, then that implies x2 minus 4 upon 2x1 minus 1 is equal to, transposing this, it will become 3, which implies 6x1 minus 3 is equal to x2 minus 4, which implies solving for x1, or let us solve for x2, that transposing this here, so 6x1 minus 4, sorry, minus 3 plus 4 becomes, minus 3 plus 4 becomes 1. This is x2. Okay, now we plug the value of x2 into the budget constraint. Okay, so we have 2x1 plus x2 is equal to this stuff, 6x1 plus 1 is equal to 73, so we have 6x plus 2x comes out to be 8x 1 is equal to, transposing this one, it will get subtracted. 73 minus 1 is 72. Dividing both sides by 8, we will get x1 will be equal to 9. Okay, so the optimal value of x1 is 9. Then the value of x2 will be equal to, plug the value of x2 in this equation, rather plug the value of x1 in this equation to get the value of x2. So x2 will be equal to 6 times the value of x1 is 9 plus 1, which gives us x2 will be equal to, x2 is equal to 9 6 are 54, which is 55. So 54 plus 1 comes out to be 55. Then x1 plus x2 comes out to be 55 plus 9, which comes out to be 64. Okay, so the value of x1 plus x2 at optimal will be equal to 64. I hope I make myself clear in this video. Thank you.